are you getting the right products? And are you getting enough of them? That's the question in selectivity. So let's look to see what we can do about this. So let's start looking at a couple of simple examples. And let's, for simplicity, let's look at examples when epsilon is 0. So no volume expansion, constant density. And let's look at a simple situation. A goes to R and A goes to S. Reaction 1, reaction 2. And let's say, this is of course the stoichiometry, then I have the kinetics. Let's assume that the kinetics are K1CA to the A here, and this is K2CA to the B here. So I have two reactions in parallel. Okay, so if I look at dC R dt, that's equal to this, and this is dCS dt. So if I'm interested in selectivity, then I would like to know roughly how much R do I make for every mole of S that I make? Or how much R do I make for every mole of A I use up? Either one of those is fine. They both give me the same information. Since these are total derivatives, not partial, I can divide these. If I divide them, I find dCr, dCs, like dt sort of cancel, is equal to K1 over K2, Ca to the A minus B. What can I see immediately? Let's say I want to make R and I don't want to make S. Well, if A is bigger than B, do I want to have A high or A low? I've gone through most of this row. So if I want to make R, and this is greater than 0, little a is bigger than little b, then what do I want to keep A high or A low? One thing at a time. If I want to, there's no question of conversion here. This is a question of, again, if you get high conversion to the wrong product, that's not very good. If you want to make wine that sells for $30 a bottle, and you get really high conversion, but you make vinegar that sells for 69 cents a bottle, you'll get fired. Okay, so we want to make sure we get the wine and not the vinegar. So if this is a positive exponent, do I want to keep Ca high or Ca low? High, because a high number means to a positive power is a high number. So that the bigger this is, the more R I get with respect to S. So if A is greater than B, then I want to keep Ca high. What kind of reactor keeps Ca high? Or as high as possible? Harder than it needs to be. What type of reactor, a CSR or plug flow reactor, keeps Ca as high as possible? These are polynomial expressions. So the rate expression of Ra versus Ca looks like this. How do I keep Ca as high as possible? CSDR means I always am at the outlet concentration, which is the lowest possible. It's exactly the opposite of what we want. Plug flow? Why plug flow?
This is the opposite of what we want.
Plug flow is not the opposite of what we want. Plug flow is what we want. Okay, there's a serious lack of understanding. serious lack of understanding. In a CSTR, I've run this 100 times. The concentration versus position here, I've got the inlet and then I've got the outlet concentration. And the outlet concentration is everywhere in the reactor. In a plug flow reactor, I draw the concentration versus position. I have the inlet, and then I go gradually to the outlet. In the CSTR, I'm at this point the whole time. In the plug flow reactor, I'm only at the low concentration at the outlet. Everywhere else, I'm higher. Let me repeat the question. What kind of reactor do we want here?
Plug flow?
Plug flow. Okay, do I want to operate at high conversions or low conversions? At least this class is reliable. If I ask a question, I just have to take your answer and take the opposite, and then I know it's the right answer.
Low conversions because you're higher CA.
The lower, if we go to low conversions, remember, I'm not interested in conversion here. I'm interested in getting the right product. The lower the conversion, the higher CA is everywhere in the reactor, and therefore the more R I'm getting relative to S. The more wine, the less vinegar. So I want to operate at low conversions. And let's say if I have a gaseous reactor, do I want to operate at high pressures or at low pressures? And why?
At low pressures because there will be gas formation during the reaction.
Anyone have another opinion?
It's gonna be okay. For lower conversion, you must operate at higher pressure because
What happens at high pressure?
your
Increase the concentration.
You increase the concentration at high pressure because you decrease the volume. So higher concentration is what we want. So we want high pressure. What if A is less than B? So that is, the reaction to S is a higher order than the reaction to R. Then the exponent is negative. Then what do I want? Do I want the concentration high or low? I want the concentration low. What type of reactor gives me a low concentration?
CSTR.
CSTR. Do I want to operate at high conversion or low conversion?
At high conversion.
High conversion. And what do I want to do with the pressure? Low pressure. What if A equals B? What if they're the same order reaction? What do I want to do with the concentration? The orders are the same. A equals B. The reaction is not zeroth order. This is eighth order, this is bth order. A and B are the same. This is not DDT. This is DCR, DCS. It's a selectivity.
You can't do it because
I can or I cannot do anything. I cannot do anything, meaning I have to just sit in a chair and I'm not allowed to do anything.
you change the function, you have the same ratio of the DCR to DCS because it's opposite. The relationship between DCR and DCS is the opposite.
The relationship between DCR and DCS, I would say, was independent of CA. That's what you were saying. So CA is irrelevant to selectivity. Just let me finish the thought. So CA is irrelevant with respect to selectivity. Then I can choose CA based on other criteria. I can choose the type of reactor based on other criteria, such as reactor volume.
What about the effects of this whole double?
I'll get to that. I'll get to that. I didn't forget. Okay, so what you can see from here is that higher concentration favors the reaction of higher order. Higher concentration favors the reaction of higher order. If R has a higher order, then high concentration, so A is bigger than B, high concentration favors the production of R. If A is less than B, that is S is a higher order, then high concentration favors the production of S. That's why I want to keep Ca low. Similarly with temperature, what we looked at earlier in the semester was with the activation energy. Higher temperature accelerates the reaction that has higher activation energy more than it accelerates the reaction that has lower activation energy. So if reaction 1 has a higher activation energy than reaction 2, I want to pump up the temperature as high as I can. If it's the other way around, if reaction 2 has a higher activation energy than reaction 1, then I want the temperature low, because that will decelerate S reaction more than it decelerates the R reaction. Any questions on that? Okay, well, let's say I extend this for a minute. To either a CSTR or a plug flow reactor, some sort of reactor. And let's say I have A plus B goes to products. So for example, if I have A plus B goes to R and A plus B goes to S. And let's say dCr dt is K1 Ca to the A1 Cb to the B1, and dC S dt is K2 Ca to the A2 Cb to the B2. dCr dCs is K1 over K2 Ca to the A1 minus A2 Cb to the B1 minus B2. So what we can see here is if I forget about B, the situation is exactly like I had before. If I forget about A, the situation is also exactly like I had before. So what happens if A1 is bigger than A2 and B1 is bigger than B2? What kind of reactor would I like in this situation? How about, who was that to? Plug. So I would like to have A and B both coming in plug flow reactor. How about A1 less than A2, B1 less than B2? So that both A2 and B2 are higher than A1 and B1. And again, here I still want R. So what kind of reactor should I use here? CSTR. Because that keeps both A and B low. Well, how about if those are of course the easy cases. What if I have A1 greater than A2, but B1 less than B2? So what would I like to do in that situation? Theoretically. What would I like to do to CA, and what would I like to do to CB?
We want to keep CA concentration high, while we want to keep CB concentration low if it's possible.
Okay, good, if it's possible. If CA is high, we usually like plug flow reactors. To keep CB low, we usually like CSTRs. How can we have A in a plug and B in a CSTR? Is there some sort of hybrid reactor we can do? Well, there's a hybrid reactor we can do that keeps A high and B low. And this is probably a reactor you haven't seen before. And imagine the following. We take a plug flow reactor where we put A in as a plug flow reactor. And that keeps A as high as possible everywhere along the reactor. But we don't want to put B in as a plug flow reactor because then B will be high everywhere. We want B to keep B low. So what if we have a bunch of little inlets along the way? And we only put a little B in at a time in each of those. So we distribute B throughout the reactor this way, but A goes in as a plug flow. So that at no point is there very much B. So this would be a way to keep A high and B low, and this is called the Zwittering reactor. Zwittering was someone's name. I think he was Dutch. I think in the 1950s, someone Dutch in the Netherlands came up with this idea for a reactor. Okay, well, this has all been qualitative and instructive. It's good to do things. Yes?
Could you also have a membrane that only lets outside types of like certain species, like if you want to keep CA high but CB low, you would only allow for it for CA species to increase in concentration?
You have to tell me more about how you do that. What your goal is to keep A high and B low. So how do you plan on doing it? With a membrane? You know, if you have a semi-permeable membrane that, let's say, lets one species through and not the other, exactly how do you want to do it? I didn't quite understand the suggestion.
So you may have a membrane that somehow drives for the gradient of concentration to increase for CA, but keep CB at a constant as it crosses the membrane.
Membranes don't keep things constant. Membranes allow one thing through and not other things. How are you going to use it to keep it constant? If you have an acid-base system, then you could buffer the concentration. If one of the reactants is an acid, then you could have a buffer. But that's nothing to do with the membrane. That's a buffer. So if you think of something, let me know. It's not obvious to me exactly how your scheme is going to get you there, but think about it. If you come up with something, fantastic. Okay, so let's see. Well, we have these qualitative quantities here. Let's see if we can come up with some mathematical functions to that we can use in somewhat general context. Notice here, in these situations, we wrote dCr dCs. And I could have also written dCr dt divided by minus dCA dt. That would have been just as good. So when I do that, and notice that these quantities depend on the rate functions. So these quantities I could write down before I choose a reactor. These are just rate functions. So, and these are of course constant density rate functions. So I'm going to define, say, phi A over B, for example. Or why don't we say phi R over A? Where R is a product and A is a reactant. Or A could be another product. And phi is I'm going to call the instantaneous fractional yield. Of R with respect to instantaneous, because it's instantaneous. I'm not talking about a whole reactor. I'm talking about, for a given set of concentrations, what exactly at that instant is the value. And this is equal to RA divided by, so it's the rate function, I'm sorry, RR, for the production of R, divided by the plus or minus RA, plus if A is a product, minus if A is a reactant, in such a way that phi is always non-negative. So I choose the sign to make this non-negative. And there's no right answer. For example, I don't have to choose phi R over S. That's no better or no worse than phi R over A, or phi R over B. They're all equally good. There isn't one like one is better than the other. It's whichever one you like better. So this depends only on the kinetics, because it depends on the rate functions. If the rate function, if the reaction is constant density, then RR is dCr dt, RA is dCA dt. If they're not constant density, then the rate is 1 over V dNA dt. Well, actually, the important thing is it's the rate function. It's the rate function with those kinetics, the K's times the concentrations, the powers. Okay, now that's the instantaneous fractional yield. Once I have a reactor or reactor system, I can define phi r over A as the overall. And this is equal to, this I also want to be non-negative, and this is equal to the outlet concentration of R minus the inlet concentration of R, divided by the plus or minus, again, depending on whether A is a reactant or a product, Ca in minus Ca out. This depends on the reactors and separators and the whole reaction scheme. Rate functions and reactors, separators, etc. Depends on the whole scheme. This depends only on rate functions and kinetics and stoichiometry. Rate functions, stoichiometry, and reactor separators. Okay, so what are some basic equations that I can come up with? If I know capital phi, I have CR out minus CR in is equal to phi R over A times Ca in minus Ca out. Where here I've written this with the sign chosen such that A is a reactant and R is a product. So if I know phi and I know delta Ca, I know delta Cr. So let's see how I get phi for CSTR. So if I plot phi, say R over A, versus, say, Ca or Xa, I get some sort of curve. Whatever that looks like. And I've got an Xa in and an Xa out. So phi depends on the concentration. Now, if, let's say I have a CSTR. If I have a CSTR, so I have Xa in, Xa out, and what is Xa in the reactor if this is a CSTR? Who's after? Who goes up to you? What is Xa here? It's after root. Did I wake you up? It's the same as it's Xa out. So that says that everywhere in the reactor, the concentration is the same. And therefore, there's some value Xa out, and everywhere in the reactor, the instantaneous fractional yield everywhere in the reactor is just the same as Xa out. Is that clear? So, everywhere in the reactor, I have Xa out. Okay, well, if everywhere in the reactor I have Xa out, then phi for the CSTR is everywhere in the reactor equal to little phi at x out. Because if you like, dCr dCs, or dCr dCa, is delta Cr over delta Ca. Because it's the same everywhere. We can just integrate. And as a result, when I plug into this expression here, I have that Cr out minus Cr in is equal to phi r over a at xa out times Ca in minus Ca out. So again, I have a graphical interpretation. The graphical interpretation here is that Cr out minus Cr in, which is what I'm interested in usually. If I don't have a separator, then what I'm interested in is how much product am I making between the out and the in. Well, whether I'm interested or not is one thing. My boss is interested in that. Customer is interested in that. So it's the area of this rectangle. It's the height at the outlet times the width, Ca, well, I should do this versus Ca. Ca in minus Ca out is equal to Ca0, 1 minus x in, minus Ca0, 1 minus x out. The ones cancel, and this is Ca0, x out minus x in. So the area here, this area, is just equal to phi times delta Ca, phi times delta Xa. So this is equal to Cr out. So let's divide this by Ca0. And then this is Cr out minus Cr in. Now, in this picture, do I want to make Cr out minus Cr in big or little? I want it big or little? I can't hear you. Do I want to make this area big or little? Little. So you want to make as little product as possible. Is that going to help you get a promotion? So what would you rather do? Unless you like being unemployed. Then you want to make as little product as possible. If you want to advance in your job, you want to make as much product as possible. So whereas when it came to tau, graphs that had tau in it, we wanted to make them small. Graphs that have product in them, we want to make them large. Okay, so we want to make this as big as possible. So here we're sort of, the way I drew the curve, we're getting a fairly small amount. If the curve went the other way, then we get a big amount. Okay, so what we've determined is phi for a CSTR. What if I have phi for n CSTRs in series? Well, if I have n CSTRs in series, can you see over here, this far in the blackboard? Okay, so I should write even further. So I have n CSTRs in series. So again, I have phi over Ca0, r over a, versus x out in. So if I have n CSTRs in series, then I know I look something like this. Same reasoning we had before. Where every rectangle is using its outlet. So this is 1, 2, 3, ... And then I can notice that I have CR out minus CR in. So out is over here, in is over here, is equal to, we said, well, let's write this out. CR out minus CR in can be written as CRN minus CRN minus 1 plus CRN minus 1 minus CRN minus 2 plus dot 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 plus CR1 minus CR in. Is that clear? All I've done is I've added 0. I add and subtract CRN minus 1, add and subtract CRN minus 2, etc. And then I can put some parentheses around these. And I can note that this is equal to phi for the nth reactor times Ca n minus 1 minus Can plus phi for the n minus first reactor Ca n minus 2 minus Ca n minus 1 plus dot 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 phi for the first reactor Ca in minus Ca1. So immediately, and since each of the phi's, big phi's, is equal to a little phi, we have that this is equal to CR out minus CR in is the sum, j equal 1 to n. So instead of rewriting the terms 100 times, I have phi, little phi r over a for concentration xj at the conversion of outlet reactor J times Ca j minus 1 minus Caj. So it's the sum of all those rectangles. And if I let n go to infinity, what am I going to get here? If I let n go to infinity, I have CR out minus CR in. If I let n go to infinity, what kind of reactor do I approach? Plug flow. So for a plug, what am I going to get here? What does that work out to be mathematically? You're not looking at your notes. You're going to fail. Next. Integral. I'm sorry? Well, let's do it in terms of x. Oh, here I've done it in terms of CAs. Okay, I did this for constant density. So I'm using CAs. So I've got CA, out, in, DCA. And we'll write the non-constant density versions next time. And we have to determine the phi. So let's just write phi now. Phi, R over A for a plug, is CR out minus CR in over CA in minus CA out. That's just equal to 1 over CA in minus CA out, integral CA out, CA in, phi, DCA. Because the numerator just comes from here. So this is for a plug. And for n CSTRs in series, just 1 over CA in minus CA out times the numerator. Numerator is this. Are there any questions on that? Questions? Okay, remember you have to look at your notes because there will be quizzes every class. Are there any questions? Okay, first I want to collect the homeworks, and second, the material for test 2 went through the recycle reactor. Once we start with selectivity, that's the material for test 3. So your homework on everything but the recycle reactor is due today. Your homework on the recycle reactor is due on Wednesday. And we're going to have a test on the material from t equals 0 to t is equal to about an hour ago on about sometime possibly next Wednesday. Might be a good time to have it. We can't have it the following Monday because some people aren't even going to be here because they're going to be at the ChE meeting. Although we will have class that Monday. Are there any questions? If people would like to have a recitation, you just have to ask me and we'll set one up. Any questions?